We're joined today in the studio by one of my most splendid students from the past, Cody. Cody, what have you been working on lately?
Well, I have been working on building a Tesla coil.
A Tesla coil.
And this Tesla coil has been giving me some problems.
What's wrong?
Well, it hasn't been working correctly, which is not good.
Right.
It just hasn't, it's been short-circuiting often.
Oh.
And so the Tesla coil, in the instructions, it gives me ways to troubleshoot. And so I've come to you to have help with the troubleshooting.
Sure. So what do the instructions say that you should do?
It says that I should use an oscilloscope.
A what?
An oscilloscope.
Oh. Well, I recognize the last part of that word as scope, meaning to see.
Yes.
So rather than getting you an oscilloscope, could I present to you some other options?
You may.
Some other scopes, maybe. How about a microscope?
No, that's for the biologists.
Okay. How about a telescope?
Well, that's just for the astronomers.
Fair enough.
Mine's much closer.
If you had a Tesla coil a long way away, that would be a good place for it, right?
That would.
How about a spectroscope?
See, that's just more for the chemists.
I suppose that's
Not going
true.
down that aisle.
I suppose that's true. Now, what about a stroboscope?
As fun as that is, and I do like dancing.
That's true. Stroboscopes!
That is more for the dancers.
Good point. Can I interest you in kaleidoscopes?
Maybe just one.
All right, I'll have one too.
All right.
Holy cow.
That is
Turn the end there.
beautiful. Oh.
Yeah. And look into the light.
Oh. All the pretty shapes.
Dang it, Cody! I thought you came here with a project.
I did. All right. The oscilloscope.
The oscilloscope. All right, how about just, minty fresh scope?
Well, no.
Okay.
That's more for the dentist. My breath is
Fine.
empty.
The oscilloscope.
Okay.
I have here a vintage oscilloscope, and I want to tell you a little bit about it. First of all, the oscilloscope has a screen right here, and it's going to read voltage as a function of time. But tell me, what's wrong with just using that? Don't you have a voltmeter?
I do.
Looks like a nice one.
Yeah, it is a nice voltmeter, but I was really more interested in looking at voltage as to really be able to see voltage as a graph for time.
So that's the action of the oscilloscope. That scope part of it lets us wait. What do you think oscillo means?
Oscillo. Maybe voltage?
No.
Really?
Then it would be called a voltascope. Nobody
That's
calls them
true.
voltascopes, though.
Oscilloscope.
This could be called a voltascope, but oscillo relates to the word oscillate,
Oscillate.
right?
Okay.
So what you're going to be seeing often on an oscilloscope, and what the oscilloscope's true power is to enable you to see oscillations in voltage. Things that are going like this. Talking about maybe simple harmonic motion, things that are going back and forth, things that are maybe alternating current, which you might need in, for instance, a Tesla coil.
Yeah.
Right? Okay, so here's the idea behind an oscilloscope. At least we've motivated why we need it, but let me go a little bit further into the history of measuring voltage. A long time ago, more than 100 years ago, this machine was built. It's a beautiful thing that's called a voltmeter ammeter. And if you hook it up to measure voltage, then it will read voltage. Now, don't you think that somebody could make a movie of that needle going back and forth and measure voltage as a function of time?
I think so.
It would be awesome. It would probably work, except that the needle is slow to respond. If you've got something that's switching back and forth 60 times per second, then you'd need to be taking a video frame weight of much more than 60 times per second. And that wasn't really possible until just recently.
Okay.
So they needed to develop something that would very, very quickly change its position. Have you ever heard of a seismograph?
I think so.
What do they measure?
A seismograph. I'm not quite sure.
What?
Earthquake.
Earthquakes. Thank you, person in the studio audience. A seismograph measures earthquakes, and you've seen these graphs where people will be like, no earthquake, no earthquake, earthquake, no earthquake, earthquake! Right? And then no earthquake.
Yeah.
Right? So this is a measure of shaking as a function of time. What they did is they put a really thin needle hooked onto a hunk of mass, and that hunk of mass is on springs, maybe isolated from the Earth. So if the Earth itself is shaking, then the mass stays still, and it creates a jigga, 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 jigga on there. That gives us a record of when the earthquake happened. That was a long time ago. So we could make voltmeters with a really, really light needle that would bounce back and forth, but we still wouldn't be able to see it fast enough. We might be able to make traces on paper. And I have a machine that traces the position of voltage as a function of time, but I don't think it responds that quickly. Like, you need to be moving the paper underneath the needle. Can you imagine?
Mm-hmm.
You'd need to be moving the paper underneath the needle really fast in order to get a graph to come off.
Yes.
What if we weren't using a needle? Something that moves even faster than a needle. Can you imagine such a thing?
Like light?
Or maybe just slightly more massive than no mass at all, an electron.
Okay.
But I like what you're saying. You're thinking that we could get our picture in light on the front of this sucker. The way this works is in the back of it, you've got an electron gun. There's a hot piece of metal, and it's spitting out electrons. And those electrons are near a negative plate.
Okay.
And the negative plate is right in front of them. And they say, ooh, I want to go to there, right? And so they do. But many of them hit the metal plate, but there are holes in the metal plate. And some of them make it right through that metal plate. And they are going, what do you think, fast or slow?
Very fast.
Very, very fast. They're going very fast. And those very fast electrons go, pew, to the front of the screen, where they meet a phosphor. The phosphor is a chemical that's coating the inside of this glass. So the electrons are captured by the phosphor's chemical reaction and converted into light. The phosphor glows. And if you'll hold this for a second, I'll show you how.
Okay.
We're back to investigate the action of a laser on this phosphor right here. Now I contend, sorry, I got a different oscilloscope. You know how these things go. So I contend that there are electrons coming from the back of this box hitting this screen and causing the phosphor to glow. And I think I can show you at least that there is a phosphor in there by this light. It's a laser, and it's primarily an ultraviolet laser. But it's got a few blue frequencies and some violet frequencies, so you're going to be able to see it a little bit on paper. Now the cool thing about this phosphor is that if I shine this laser, which is definitely not green, on the screen, then it appears as a green dot. What do you think, Cody?
It looks green.
Also, and what Cody can vouch for, I hope, is that there's a slight lag. Like, you can kind of see where it was. And if you ever had glow-in-the-dark stickers or glow-in-the-dark shirt when you were a kid, if you put light on that sucker, it would continue to glow for a little bit. I would call the stuff that's in that paint a phosphor also.
Okay.
So that's the action of the oscilloscope that's going to do that for us. Now, modern oscilloscopes do not have what I'm going to describe. They are simply a device for recording digitally the voltage at every moment in time, because digital processors are so fast now. They record the voltage digitally as a function of time, and they show it on a screen, just like a smartphone. In fact, you can take a smartphone and turn it into an oscilloscope with some software and your headphone jack. Pretty awesome.
That is pretty awesome.
But it's easy to ruin your smartphone that way. Like if you hook it up to the wrong wire while you're testing your Tesla coil, for instance. So better to have a dedicated oscilloscope, because there are circuits in here that protect it from fires and explosions and stuff.
Yes.
So there's a phosphor inside of old oscilloscopes, and old oscilloscopes still are really, really powerful. In fact, they have a lot of advantages over the newer and cheaper digital storage oscilloscopes. But the same could be said for the new ones. The new ones are really, they do some other things very nicely too.
Okay.
But we're going to be talking now about what's called CRT oscilloscopes. Can we even see that? I don't think we can see that. There. Now we can see it. All right. So we're talking about cathode ray tube oscilloscopes, and some people just call them CROs, or cathode ray oscilloscopes. So what we've got here is a hot piece of metal, as I described, and that hot piece of metal is sending electrons towards the screen, and the screen is positive, and the electrons say, ooh, let's go that way, and some of them make it through. So when they get here, they're going very fast that direction. And if unimpeded, they would all hit in a dot in exactly the center of the screen. And if you turn on an oscilloscope, well, in some settings, you would have just one dot at the center of the screen. We'll talk about what an oscilloscope looks like natively when we get over there. But first, I just want to talk about a stream of electrons coming this direction. There's lots of electrons, and they're all going this way. You see, this is a zoomed-in picture of this part of the tube. This is where the business is happening, right in here. So our goal here is to figure out what we could do to make these electrons go either up or down.
Okay.
You thinking what I'm thinking?
Magnet.
Maybe. You just created television. But even simpler, just electric charge.
Okay.
Right? Because electrons want to go away from negative charge and towards positive charge. So let's make a plate of metal actually above the beam of electrons and another plate of metal below the beam of electrons, parallel to one another like this. Connect those suckers to wires. And then, if the voltage is positive, like I would say, if the positive side is up, then these electrons will curve towards it while they're in there. And then they'll go in a straight line. So this would be what happens if the positive side is up. And then, if the positive side is down, then the electrons would go this direction. They would be curving in here, and then once they get out, they just go in a straight line because they don't feel the electric field anymore. This would be the case where positive is down. So in that way, we can control where the electrons go up or down. There's also an oscillator inside of the oscilloscope. Go figure, right? And the oscillator is causing this dot that would be present to start at the left and go to the right. And it sweeps it across the screen at a rate that's determined by some knobs on the front. So it just goes shoo, 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 shoo. So it's always ready to display voltage data.
Okay.
And you can have it sweep very slowly. You can actually have it just go, or you can have it go shoo, 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 shoo. So we're going to get into an oscilloscope in our next video. Let's go. A telescope!
Well, that's just for the astronomers.
Fair enough.
Mine's much closer.
If you had a Tesla coil a long way away, that would be a good place for it, right?
That would.
How about as scope, meaning to see?
Yes.
So rather than getting you an oscilloscope, could I present to you some other options?
You may.
Some other scopes, maybe.
Okay.
How about a microscope?
No, that's for the biologists.
Okay. How about...
And so I've come to you to have help with the troubleshooting.
Sure, sure. So what do the instructions say that you should do?
It says that I should use an oscilloscope.
A what?
An oscilloscope.
Oh. Well, I recognize the last part of that word.
Yeah. Problems.
What's wrong?
Well, it hasn't been working correctly, which is not good.
Right.
It just hasn't. It's been short-circuiting often.
Oh.
And so the Tesla coil, in the instructions, it gives me ways to troubleshoot.
We're joined today in the studio by one of my most splendid students from the past, Cody. Cody, what have you been working on lately?
Well, I have been working on building a Tesla coil.
A Tesla coil.
And this Tesla coil has been giving me some